Hi students, welcome back to the online video lectures on DSP. So this is the third lecture on sampling. In the last two lectures, we have seen given a continuous time signal, how do you get mathematically an equivalent discrete time signal, right? And what are then the relationships between the Fourier transform of discrete time Fourier transform of the output signal versus the the continuous time Fourier transform of the input continuous time signal, and also relationships with the intermediate signal that is obtained after multiplying the original continuous time signal with an impulse train. So these are what we have roughly seen in the last couple of video lectures. Uh, what we would be doing in this current video lecture is, given a discrete time signal, how do you reconstruct a continuous time signal? How do you get back a continuous time signal? And as we mentioned in the earlier class, what we would be interested looking at are in fact band limited signals. That means you could say which is the cutoff frequency as the upper frequency that is there, beyond which there are no frequency components in the given signal. Okay, with this background, let's this also most of the lecture I would work out on the notebook, as it involves the like doing the mathematical derivations and the other stuff. Okay, let me now move to the desktop sharing mode and then to the one notebook stuff. Okay, let me just make it. Okay, so let me first give again a block diagram of the whole process, right? Let me start with the block diagram of the whole thing. Assume that you have an xc of t signal. Okay, there is this continuous time signal, which earlier we wanted to get a discrete time equivalent of the continuous time signal. You multiplied with an impulse train. What you got out of it is, we called it as xs of t. Okay, and then there is in fact integration going on, but to keep things simple, let's write it as a to d conversion is what you are doing here, right? And with that, we have arrived at a signal which is x of n. This is what we have discussed so far. Now assume that this we are giving to another digital to analog conversion. Okay, you could think of it as an impulse generator with which you multiply, and what you get out of it, you call it as xs of t again. So you are getting back that signal. Okay, now again assume that this digital to analog conversion is done already. Xs of t is there. You want to give it to a filter that does reconstruction of the signal. Okay, so this is let's call it as a reconstruction filter. This is reconstruction filter, out of which you are getting, let's say, the reconstructed signal xr of t. Since you are not doing in between other than this analog to digital and digital to analog conversions here, what would you expect here is, provided there is no aliasing and other things, but you would expect this to be equivalent to xc of t. That's your expectation, right? And the first block, still x of n, we have already discussed in the last couple of classes. We would now focus more on this part. Okay, this which I am keeping in the dotted lines, this is what would be particularly discussing in this class. Right, now let's start. Given x of n, you want to get xs of t. So what exactly needs to be done? So you have signal values at n equal to 0, 1, 2, 3, 4. Now this also, by the way, unless you have the information of at which rate these samples have to be placed, there is no way you could do xs of t. So I'm additionally keeping here another input to this converter where I will mention the sampling rate that essentially comes from this s of t. Whichever rate at which you have sampled, that information has to be fed to this digital to analog converter. So assume that you know this value, then how do you get xs of t from xn of t? All you need to do is each, for example, x of 0 will be at xs of 0, x of n will go to xs of capital T. Now x of 2 will go to x subscript s of 2t, and so on. So that is nothing but I could write that relationship as n varying from minus infinity to plus infinity, x of n, this value has to come at nt, right? When n is 0, that value should go to x subscript of 0. For example, n equal to 4, that should go to x subscript s of 4t. So this is the expression, this is the important expression, right? Now you know xs of t. What you would like to get now is xr of t. Okay, that how do you know that? See again, let me remind you what's the property that we have for an LTI system and what it means by impulse response. So suppose if I have an LTI system to which the input is delta of t, okay, particularly that recon filter is what, reconstruction filter is what I would like to see. So if its impulse response is hr of t, what does that mean? If I give delta of t as input, I would be getting hr of t, correct? Because its system response is given as hr of t. Suppose instead of that, now if I give as input to the same system, same LTI system, okay, delta of t minus nt, if that is what I am going to give, what would be the output? This being linear and shifted invariant, obviously I should get as output hr of t minus nt, right? Now keeping this in mind, now take a look at the value of xs of t, and it has summations of shifted impulses that are each one is scaled by value of x of n. So you could now in a position to say what would be the reconstructed signal xr of t would be. Obviously, so delta of t minus nt, you will have hr of t minus nt. So this is equivalent to n varying from minus infinity to plus infinity, x of n into hr of t minus t. Another important relationship. Okay, that's xr of t in terms of x of n. Make a note here, we still haven't said anything about what exactly is hr of t as such. That's what we would be are working out now. So now let's do the computation of hr of t is what we will do now. So let's do now computation of hr of t. Okay, that's what we will do now. Well, how can we get that? We know the frequency spectrum of xs of t. This we have worked out in the earlier classes, right? And this you assume that this is a band limited signal xc of t with omega n minus omega n, this being 1. Okay, now we expect the same thing, and then let's first treat it from the point of view of frequency spectrum. Okay, so let's first plot xs of j omega, right? What would that be with respect to xc of t? We have discussed in the earlier classes. This gets scaled by a factor of 1 by t instead of 1 in the y-axis, okay, the magnitude value, and on the x-axis you get multiple copies of it, each copy placed at integer multiples of omega s, omega subscript s. So that's how it would be. So this would be, for example, there we assumed it to be t was 1, so this would be 1 by t. Okay, this of course will be at omega n and minus omega n. Now also assume there is no aliasing, so enough spacing is there. So now copies, next copy would come at omega s, okay, and other copy would come at 2 omega s, and so on. And similarly this side also I'll have a copy at minus omega s, minus 2 omega s, and so on. And this would be magnitude of xs of j omega, right? Now I want, so how do I get from here the magnitude spectrum of xc of j omega? See, basically hr of t, we want it to be equivalent to the original continuous time signal with which we have started, right? So how do you get that out here? There are, as I mentioned, one thing is you need to retain only one copy, okay, and another thing is you need to make correction for the amplitude. So that means these are the you just get rid of the high frequencies here, okay, you just retain the somewhere, this is the only copy you want it, so you apply a low pass filter here. Okay, what should be the multiplication factor of this low pass filter? Should be t, so that the magnitude would be same as 1, which is for the xc of t. Okay, and now what I should do is, you have some cutoff frequencies here from minus omega c to plus omega c, taking care that other copies are getting rid of those copies. So once you do it, so this is what is your let's say this is which filter should do this now. That's exactly the job of this hr of t. So now we have in the magnitude spectrum, now we know that is x hr of j omega magnitude. This is what you wanted, and as a result, multiplication of both, what would that give you? That in fact gives you till from omega n to minus omega n is getting 1. Okay, this is what you would be getting as magnitude of xr of j omega, the reconstructed signal. This is what you would be getting. That's what it is. So from here you know that this is your low pass, this essentially is the low pass filter. Okay, and then is there anything else here to be figured out? Is that what should be the cutoff frequency? Okay, that's something we have not yet worked out. So let's take a look at what should be the cutoff frequency in radians per second, that omega c. That's what we will work out now. Here, for example, this value, this is where you have a cutoff frequency omega c. This value is omega s minus omega n, correct? So that should be, cutoff frequency should be in between omega n and omega s minus omega n. That's one condition. Okay. Is there any other condition? Yes. To avoid aliasing, we have a condition on omega s. That's what is there. Omega s should be greater than or equivalent to 2 times omega n. Okay. What's done here is, take a look here. So this side omega, if you look at in between, what's happening in between 0 and omega s, somewhere in between you have to take it, such that it doesn't either come in between 0 to omega n or omega s minus n to omega s. So usual value is taken is exactly in the middle. This is taken. So commonly used choice, the commonly used choice for this omega c is omega s by 2. This is the commonly used choice. Okay. Well, we know omega s in terms of 2 pi by t also. So this is nothing but omega s is 2 pi by t into 1 by 2. Okay. So that implies the commonly used choice for omega c is equal to pi by t radians per second. To take half the way in between 0 and omega s. Okay, hope this is clear. That's what, so the typical choice is here, you have pi by t. This is of course minus pi by t. This is anyway t. Is that clear? That's the common choice. Okay, you could also see here, to avoid aliasing, this is the case. So this omega s by 2, I could say, should be greater than or equivalent to omega n. So usually when there is no aliasing, this comes more than this value but less than the other one anyway. Okay, clear. Okay, this, what we did so far is we managed to now get hr of j omega. Okay, now let's take so from that, now let's compute hr of t. We know now how hr of j omega looks like. Our hr of j omega is, now we got it, is what is this function called? Rect function. This is your omega magnet. So this is your hr of j omega. Okay, this is from pi by t to minus pi by t. This magnitude is t. Okay, so if you want to mathematically represent that, this is equal to t when omega is less than or is in between minus pi by t to plus pi by t. Okay, and this is 0 otherwise. This is your CTFT. Now, well, you could compute the inverse continuous time Fourier transform. So your hr of t would be equal to 1 by 2 pi integral over minus infinity to plus infinity, but anyway this is non-zero from minus pi by t to plus pi by t only. Let me keep that itself, and during that hr of j omega I need to write its value as t into e power j omega t I should finally get in terms of t, so here d omega should be there. Okay, this value is equal to t by 2 pi e power j omega t by integrating with respect to omega, so jt would come here. The limits for this are minus pi by t to plus pi by t. Okay, so this cos omega, so this is equal to t by 2 pi into 1 by jt into e power j times, you have to substitute in the place of omega, right, j times pi by capital T times t minus e power minus j times pi cap by t into t. Okay, so this will give 2j times a sign, and that 2j and this 2j would get cancelled out, so that would give you eventually hr of t is equal to sine of pi by capital T times t divided by, let me bring that denominator into the denominator of the denominator. Okay, that would give me pi by t times t. You already know this function. In fact, you already studied this rect sync in detail earlier in your signals and systems course. Okay, this is how it is. So that's the reconstruction function or reconstruction impulse response. You use it. Sync function is what you use here in order to get back your xc of t there. Okay, that's the hr of t. So how does that look like? You know, okay, so we are this is time domain, so this is t. It has, its value would be 1 at 0. Okay, any idea on this? So this, if I remembered correctly, this is 1. Okay, you could check it out. Any guess on what this, where it will have zeros? This is at t, 2t, 3t, 4t, and so on. So similarly here, minus t, minus 2t, minus 3t, and so on. Okay, so that's the nice property here. Only at multiples of the sampling rate you have its value to be 0. Okay, now this is your hr of t. So we got all expressions pretty well here. We got hr of j omega is this expression, and that's your hr of t. Okay, now with this, let me now write, okay, interpretation of now you got the impulse response. Let's make interpretation for now. What is, how you are getting back xr of t from xs of t. That's what we will now do. Okay, so what we will do now is interpretation of xr of t. This is what we will do now. Let's first write the expression for it. What is the expression for xr of t? Did we do something related to that earlier? Yes, this is the one. So that's nothing but summation. Let me rewrite it here. This xr of t is equal to n varying from minus infinity to plus infinity, x of n into hr of t minus nt. Right, now you already know hr of t. to substitute that there. So what would you get for XR of t? It's equal to summation over n equal to minus infinity to plus infinity x of n into sine of pi by capital T into t minus nt by pi by t into t minus nt. This is another very important expression for the reconstructed signal in terms of the input discrete time signal. Okay, you could see here x of n is multiplied with a shifted sinc functions, and for each given n, that is shifted to n times t location. Okay, this time I would like to give you some relief from my own drawings, and let me copy paste it there. Okay, instead of drawing it myself. Okay, yeah, look at here how this is. It's important you have some intuition about how exactly is this able to do this, right? So you have a continuous time signal xe of t. Okay, and then what we have done is xs of t is obtained by retaining its values at integer multiples of that capital T, and from that you want to reconstruct back your xc of t. So the reconstructed signal is xr of t. So notice here its values at integer multiples of t are correct values only at in between it has to fill. Now it has no idea on what's the values in between. So what it does is, when you have the sinc function, already I mentioned that at integer multiples of t this is 0. So this n, when you have the sinc here, it doesn't contribute any value at integer multiples of t. In other words, it just retains whatever is there at that point, non-zero value, but it all of them will have non-zero values in between these integer multiples, and this shifted versions are taking care of that, and multiplication with x of n is taking care of retaining its correct values at integer multiples of t. So that's the interpretation I would say for this one. So yes, so that's I would say we are done with this now. So we started with just a quick recap. We started with x of n here, and we expressed xs of t in terms of x of n, then xr of t in terms of x of n. Okay, and then we worked out what should be the hr of t, so that you could get the frequency spectrum of xr of t from xs of t, and that is how we designed the low pass filter here. Okay, and after getting that low pass filter magnitude spectrum, we have done the its time domain function, what it should be, hr of t we computed here. Okay, once you have hr of t, and then essentially convolving hr of t with xs of t would give you the same thing we have written as scaled and shifted versions of this thing. So that's another way. It's a simple convolution is another way you could look at it. This is nothing but convolution of x of t, xs of t with that. That's also the way you could look at it out. Okay, hope this is clear. If so, I'll just maybe I'll stop this video here, because this has some let me just move to here. Okay, so I'll stop this video here. What I will do is I would like to solve a couple of problems that I will do as part B of this video, part B of part 3. Okay, this is part A of part 3, so that this you will have some time to clearly contemplate on that, and then we will look into this in the next maybe some 20 minutes video, 15 to 20 minutes video, where I will solve a problem and give you a couple of exercises for you to work out. Okay, let's stop here. Yeah, thanks.